Before we start, I want to count up all my dots so I know how many dots are in my total sample space. So in my sample space, if I count them up, I have 15 dots. So the number in my sample space is 15. So let's start. Probability of being in circle A. Well, circle A is right here. So how many are in circle A? 1, 2, 3, 4, 5, 6, 7, 8. 8 out of a total of 15. 8/15 is the probability of being in circle A. Probability of being in circle B. Now it doesn't say only in circle B, so this part over here counts too. So the probability of being in circle B, there are 6 things there. So that's 6 out of 15, which reduces to 2/5. There are 2 ways to do the next one. The complement of A, the probability that you're not in A. Well, the probability of the complement is going to be 1 minus the probability that you are in A. So that's one way to do it, 7/15. The other way to do it is to highlight all the stuff that's not A and count up how many dots are there. 1, 2, 3, 4, 5, 6, 7. Again, 7, that should be 7/15. Next, probability that you're not in B. Well, the probability that you're not in B is 1 minus the probability that you are in B. So 1 minus 2/5 is 3/5. The other way to do that is to highlight all the things that are not B. Okay, there's the circle B. There's the highlighted portion that's not circle B, so count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9/15, which reduces to 3/5. Again, either way, 3/5. Okay. So now probability that you're in A or B. So that means you can be in A or in B or in both. That's this picture right here. The probability that you're in A or B. How many things are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 out of 15. Number 6, probability of being in A and B. That means that you have to be in A and B at the same time. So that's this piece right here. A and B. Okay, there are 3 dots there out of a total of 15. So 3/15, or that reduces to 1/5. Probability of A given B. Well, if you're given B, what that does is it reduces your sample space. Now your sample space is only B. So the highlighted portion there, only B. So how many things are in my sample space now? 6. So I have 6 things in my sample space. Now what's the probability of those 6 that they're in A, circle A? Well, those 3 right there are in circle A. So that's 3 out of 6, or 1/2. Similar problem. What's the probability that you're in circle B given that you're in circle A? Well, let's see. So again, that's reducing your sample size given that you're in A. So now our sample size is how many things are in A? 1, 2, 3, 4, 5, 6, 7, 8. 8 things in A. Out of those 8, what's the probability that you're in B? Well, those 3. So that's 3 out of 8. Probability that you're not in A and B. Okay, so one way to do that is just to do 1 minus the probability that you are in A and B. The complement will always be 1 minus. So that would be 1 minus probability of A and B is 1/5. So that's 4/5. Another way to do that with just using the picture is to go up and say, okay, the probability that I'm not in A and B. Well, A and B is that little slice there. So if you're not in that little slice, you're in the rest of the picture. So how many dots are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12 out of 15, or 4/5. So either way, you get the answer of 4/5. Okay, let's look at probability of the complement of A or B. So you're not in A or B. Again, one way to do that is to do 1 minus the probability that you are in A or B. We know that from above. 1 minus A or B, that's right here, 11/15 is 4/15. But we can get that from the picture too. If you look at A or B, that's all A or B or its overlap. Well, what's not A or B? That area, 4/15. Again, the answer is 4/15. Choosing if two events are dependent or independent. Independent means that A does not affect B happening. So they don't affect each other. So tossing a coin and drawing a card from a deck, those don't affect each other, so those are independent. B, drawing a ball from an urn, not replacing it, and then drawing a second ball. If you don't replace it, that adjusts the sample size. That affects the probability of drawing the second ball, so that's dependent. Not replacing is always dependent. Getting a raise in salary and purchasing a new car. Well, if you get a raise in salary, you might be a little more likely to purchase a new car because you'll have more money. So those are dependent. One could affect the other. D, driving on ice and having an accident. Well, if you drive on ice, you are probably more likely to have an accident. You could be more likely, so those two events are dependent. E, having a large shoe size and having a high IQ. Those do not depend on each other, so that is independent. Number 2, which is actually problem number 8. It is reported that 72% of working women use computers at work. So the probability of using a computer at work is 0.72. Also, the probability of not using a computer. Actually, I don't think we need that for this problem. So notice that I've done part B first. The probability that all 5 use a computer in their jobs. So the probability that I pick one person, they use a computer, and then I pick another person, they use a computer, and then another computer, we're going to multiply those probabilities. So the probability that the first person uses a computer is 0.72, and then the next person, 0.72, and then the next person. So 0.72 to the 5th power, or 0.72 times itself 5 times, is 0.193, rounded to 3 decimal places. So now let's say, okay, at least one person does not use a computer. So of those 5 people I picked, at least one of them doesn't use a computer. That probability is hard to find because I would have to figure out the probability that the first person doesn't, the second person doesn't, or the third person doesn't, or the first and third person don't, or the first. There's a lot of different choices. So what I do instead is I say, okay, at least. That means 1 minus the probability that they all do, which we just figured out. The probability of drawing 2 cards and without replacement, that's key, without replacement, and both are spades. The probability that the first one is going to be a spade is 13 out of 52. And then, so I multiply the second card. Well, the first card was already a spade, so that means there's only 12 spades left. You always assume that the first thing happened when you're figuring out probabilities like this. And so now that you took a card out, now you have 51 cards. So the probability that both are spades is 1/17. Okay, now think about that. If both are spades, that's going to be the same probability for both our hearts, both our clubs, both our diamonds, right? So that comes into play in part B. Both are the same suit. Well, that's going to be the probability that both are spades. So both spades, or, so plus, the probability that both are hearts, plus the probability that both are diamonds, plus, that's supposed to be a diamond, the probability that both are, what am I missing, clubs. Anyway, those are all going to be 1/17. Plus the probability that both are diamonds, plus the probability that both are clubs. So that's going to be 4/17. Again, I'm just taking this number and saying, okay, that could happen 4 different times, once with each suit. Okay, part C. Both are kings. Well, you times the probability that the first one would be a king. There's 4 kings out of a total of 52 cards. And then, given that that happened, what's the probability that the second thing happens? Again, this is without replacement. Well, if I drew a king, that means there's 3 kings left out of a total of 51. So I multiply those two fractions, and I get 1/221. Problem number 4, which is problem number 12. A flashlight has 6 batteries, 2 of which are defective. So what's the probability of being defective? 2 out of 6, right? So if 2 are selected at random without replacement, find the probability that both are defective. Okay, so I don't replace them. So find the probability that I get 1 defective and then another defective. So, and then I multiply. So the first one is 2 out of 6. And then, so I multiply. The second draw, well, I'll only have 5 batteries left, and I will have already taken out 1 defective one, so there will be 1 left. So that's 1/15. Number 5 gives the hint, draw a tree diagram. So we've got 2 models of an item. Model 1, which is 80% of unit sales, and Model 2, which is 20% of unit sales. So there's my 80% chance Model 1, 20% chance Model 2. Then I know that some of these are defective. 10% of Model 1 is defective, and 18% of Model 2 is defective. 10% Model 1 defective, that means 90% is good. 18% of Model 2 defective, so 82% is good. So now to find out what the percentages are for each of these, I can just take, so let's say I wanted to know Model 1 defective. I would take 0.8 times 0.1, that you're in Model 1 and then you're defective. So that's a 0.08 or 8% chance of being Model 1 and being defective. I can do the same thing here. 80% chance and then to be Model 1 and then 90% chance of being good. So 72% chance of being Model 1 good battery or good item. Same thing here. 20% chance of being Model 2 times 18% chance then of being Model 2 defective gives you 0.036, or a little under 4% chance of being Model 2 defective. So this is the percent chance that you're Model 2 but good. If I add all these numbers, I should get 1. This is 100% of the options that could happen. So they want the probability that if I just pick one thing that it's going to be defective. Well, where's the defective ones? Here and here. 0.08, model 1 defective. 0.036, model 2 defective. So when you add that up, you get a 0.116 altogether of being defective. 3 rolls of 2 dice. Find the probability that you get greater than 9 on the third try for the first time. So you don't get greater than 9 on any of the other rolls. So first off, go to your sample space for rolling 2 die on your formula sheet. You'll see there that there are 36 items in your sample space, and you can also look at the sums. So before we even start this problem, I want to know what's the probability that I get a sum greater than 9. So find the sums for 10, 11, and 12. There's 5 of them, right? 1, 2, 3, no, 6 of them. So 6 out of 36, that's the chances that I have a sum greater than 9. Again, I'm counting these up off of the sample space on my formula sheet. So what's the chances then that I'm going to get a sum less than or equal to 9? Well, if 6 were greater than 9, then that means that 30 of them were less than or equal to 9. And again, I could count up those 30 on my formula sheet. So these reduce to 1/6 and 5/6. So now let's attack our problem. So we want the probability that the first dice is going to be less than 9 or some. That's 5/6 chance. And then less than 9 again, another 5/6 chance. And then greater than 9, a 1/6 chance. Multiply those 3 fractions and you get 25 over 216, or 0.116. Number 7, which is problem number 25. I have to tell you that I actually did this problem wrong the first time I did it. I actually did too much work. A circuit to run a model railroad has 8 switches. 2 are defective. So here's what I did. I thought they wanted the probability that the first switch you picked and then the second switch you picked were defective. So I did, okay, the probability that you pick the first switch defective, that's 2 out of 8, times then the probability that the second switch is defective, given that you picked a defective one on the first one. So if you picked a defective one on the first one, you've got 1 defective one left out of a total of 7. So then I thought, oh, okay, you've got 2 out of 56 for a probability. But actually, then that is not right, because what does the question ask? It only asks for this. Find the probability that you pick a defective switch on the second try, given that you picked a defective switch on the first try, which is just this. It's just this piece of that problem. That's the probability that you get a defective switch on the second try, given that your first one was defective. 1/7. When I did this problem, number 8, which is actually problem number 27, I had to go and use this formula from my formula sheet, which says the probability of B given A is the probability of A and B divided by the probability of A. So then the probability of being calculus and being on the Dean's List we know is 0.042. So B and A, or A and B, is 0.042 divided by the probability of A, probability of being on the Dean's List, 0.21. And that will be the probability of B given A. That'll be the probability of being in calculus given you're on the Dean's List. 0.2, 20%. You have to use the formula for that one. The first thing I do when I get problems like this is total up the totals. So first I'm going to total up how many males I have by adding the male row and females by adding the female row. Then I'm going to add up how many people I have in pathology, pediatrics, and psychiatry by adding their columns. Then finally I'm going to figure out what is my total number in my sample space. Now to do that, I can either add the total male and female to get my total number of people, or I can add these three numbers to get my total. Both of those should add to the same number. Actually, I do both to make sure I haven't made a mistake in my calculations. So now, the probability that you are male given that you're in pediatrics. So again, this reduces our sample size. Pediatrics, I'm only looking at these people. So what's the probability that I'm male given that I'm in pediatrics? Well, the sample size, how many people are in pediatrics? 66,371. And how many of those are male? 33,020. Or when I change it to a decimal, I get 0.498. So now, the probability that I'm in pathology given that I'm a female. So now I'm given that it's a female. So that's these people. So the total in the sample space is 51,247. That's all the females. So given that it's a female, what's the probability of being in pathology? Oh, pathology is 5604. As a decimal, that would be 0.109. To make sense of this problem, I'm going to go back and look at the multiplication rules. If two events are independent, you find the probability of A and B by doing the probability of A times the probability of B. But if they're dependent, you find that probability by taking the probability of A times the probability of B given A. So in order for events to be independent, if you figured out this probability, it would have to be the same thing as the probability of B, because that's when events are independent. Well, the probability of being in pathology is 18,179, pathology, out of a total of 124645, which is 0.146. If those were independent, then this probability would be the same as this probability because they'd be independent events. And since this is not the same as this, then they are dependent. So no, these are dependent. Before I start number 10, I'm going to figure out a few things. The first is I'm going to write down from the problem that the probability that the accident was caused by driver error is 0.54. So then another helpful thing for me, well, what's the probability that it's not? To find the complement of that, I take 1 minus that probability and get 0.46. So not caused by driver error is 0.46. So 3 accidents are chosen. What's the probability that all are caused by driver error? So what's the probability that the first one is, and then the second one is, and then the third one is? What's the probability that none are caused by driver error? So that would be the probability that the first one isn't, and then the second one isn't, and then the third one isn't. The probability that at least one is caused by driver error. Again, that is a really hard probability to figure out because you'd have to figure out the probability that So you'd actually have to figure out, if you did this directly, you'd have to figure out all these situations and all their probabilities. The first one error, the second two not. The first one not, the second one error, the third one not. The first one error, the second one not, the third one error. All three of these, you have to figure out all these probabilities and then add them together. We could do that, but it takes a long time. What I'm going to just do is figure out this one case, not. We already have that. And then I know that these are going to be 1 minus the probability of no error, no error, no error. So 1 minus 0.097 or 0.903. Three letters are chosen. Find the probability of at least one x. Again, I'm not going to find at least one x. I'm going to find the probability that there's no x's and do 1 minus. So I know the probability of getting an x is 1 out of 26. So the probability of not getting an x, or the complement of that, is 25 out of 26. So I want to know the probability that I get no x's. So if the first one is not an x, first letter I draw, and then the second one is not an x, and then the third one is not an x. That's point. So this is the probability that I get no x's in my 3 draws. So what's the probability that I get at least 1? 1 minus that. .111.